When a fluid is flowing through a pipe, the fluid will experience certain resistances due to which some of the energy of the fluid will be lost. So students, today we are going to discuss about the different energy losses or head losses that can occur in a pipe through which a fluid is flowing. So the loss of energy is classified into two basic groups. One is major energy losses and the other one is minor energy losses. So the major energy losses involves the energy loss or head loss only due to friction. Okay, friction between the flow of the fluid and the pipe, right? So major energy losses is given by two formulas. One is Darcy-Weisbach formula and the other one is by Chase's formula. So let's see what the Darcy-Weisbach formula says. So the loss of head in pipes due to friction by Darcy-Weisbach formula is given by this expression or this equation, where HF denotes the loss of head, which is equal to 4 into F LV square divided by D into 2G. So these terminologies also are very clear. F means the coefficient of friction, L is the length of the pipe, V is the velocity of fluid flow that is occurring through the pipe, D is the diameter of the pipe cross section, and G is G is known to everyone, that is the acceleration due to gravity. So as simple as that. Next, we have the Chase's formula for deriving the loss of head due to friction between pipe and flow. And the formula is given by this, where HF is equal to F dash divided by rho G into P by A into L into V square. So F dash again is the coefficient of friction according to Chase, or given by Chase, divided by rho G. So what is rho G? Rho is the density of the fluid that is flowing, and G is known to all. It is the acceleration due to gravity. Now P, what is P? P is nothing but the weighted perimeter of the pipe. See students, today we are discussing the loss of head or energy losses inside pipe through which a fluid is flowing. Okay. So what is our weighted perimeter? Weighted perimeter is the total inside perimeter of the pipe along which the flow is taking place, right? It is the perimeter of the pipe along which the flow of fluid is taking place. So if suppose we have a pipe, I will show you. Suppose this is our pipe, okay? This is the cross section of the pipe and this is the length of the pipe, and my fluid is flowing up to this much, okay? Fluid is only flowing up to this much, okay? So what will be my weighted perimeter? The half of this pipe, the upper half of this pipe, there is no fluid flowing through this upper half. Only fluid is there in the lower half of the pipe. In that case, what will my perimeter be? My perimeter will be the perimeter of this half pipe, half the cross section of the pipe, right? So this is my weighted perimeter. Okay, so area is nothing but the total area of cross section. Total area of cross section is this entire cross sectional area. Okay, then we have L. L is the length of the pipe. Everyone is aware, or it is known to everyone what is the length of the pipe, and V is the velocity of the fluid flow through the pipe. So these are the two basic equations with which you will be able to calculate the energy losses occurring inside a pipe only due to friction. Now in the next category, we have the minor energy losses, and minor energy losses will occur due to expansion or contraction in pipe, okay, or due to bendings or fittings of pipe, or if there is a certain contracted portion in your pipe. In such cases, minor energy losses will happen. So let's see what are the types of minor energy losses. Okay, so minor energy losses is subcategorized into 7 different cases. Okay, let's go through these cases one by one. So first we have the sudden expansion, or the loss of head due to sudden expansion of pipe. Okay, see, See, observe this pipe. See, in this region, the diameter or the cross section of the pipe is smaller. Then the pipe at a certain point has undergone a sudden expansion in size. Okay. So what happens after this expansion? The diameter or the cross section of the pipe has increased to some extent. In that case, what will be the loss of head? Now, suppose if I mark this smaller cross section with uh, a certain section, that is 1, and then the larger cross section, if I mark it, if I make a section, suppose, and demark it with 2, then the velocity of flow through this section 1 is v1, and obviously due to the expansion in the pipe, the velocity will change, it will get altered, and the section which is passing through the larger diameter is marked as 2, and the velocity through this larger cross section is v2. So in that case, what will be my head loss? The head loss will be equal to v1 minus v2 whole square divided by 2g, right? So next case is the loss of head due to sudden contraction in the pipe. Now, if you observe this pipe, see, there is a at a certain region or at a certain zone, there is, the pipe has undergone a certain contraction. Okay, what does the sudden contraction it means? It means that there is a sudden change in diameter or change in area that happens in the pipe, right? So initially what happens, initially the diameter or the area of the pipe was bigger, then due to a sudden contraction, what happens, the diameter or the cross section of the pipe has contracted very much. Okay, it has undergone contraction to a certain extent. Then again, after the contraction region has been overcome, the pipe of the diameter or the area of the diameter again increases, but the increased diameter is lesser than the initial diameter of this pipe. So this enlarged diameter, the biggest diameter or the initial section, the initial cross section of the pipe has been marked by a section 1. Then the contracted region has been marked by a section given by C, and the final decreased diameter or the final decreased area of the pipe has been marked by a section 2. So this derivation of loss of head due to sudden contraction in a pipe is a big derivation, but even after deriving the entire loss of the entire value, the value of loss of head for pipes with sudden contraction, the head loss is derived to be approximately this value. Okay, so this is the approximate value of the head loss which has been derived for pipes undergoing sudden contraction, and it is given as 0.5 times v2 square divided by 2g. Okay, so what is v2? V2 is the velocity of pipe velocity of fluid flow through pipe in this cross section. Okay, so next we will see the third case, that is the loss of head due to at the entrance of a pipe. So the third, this is a third case, which is loss of head. This is a third case, which is the loss of head at the entrance of a pipe. So this is the loss of energy which occurs when a liquid is trying to enter into a pipe, which might be connected to a large tank or maybe a reservoir. So this loss, that is the loss of head at the entrance of a pipe, is similar to the loss of head due to sudden contraction, and this loss depends on the form of entrance. Okay, so for a sharp edge entrance, this loss is slightly more than a rounded or a bell-mouthed entrance. In practice, the value of the loss of head at the entrance of pipe is taken as 0.5 times v square by 2g, where v is the velocity of the liquid flow in pipe. Okay, next, the fourth case we have is the loss of head at the exit of a pipe. So this is the loss of head or the loss of energy due to the velocity of liquid at the outlet or at the exit of the pipe. Okay, so what happens when the liquid that is flowing through a pipe is getting dissipated either in the form of a free jet, or it is getting lost in into a tank or a reservoir, this kind of loss of head will happen. Okay, so this loss, that is loss of head at the exit or the outlet of the pipe, is taken as equal to v square by 2g, where v is what? V is the velocity of the flow at the outlet of the pipe. So this is very important. Please mark or write it down. So v is equal to velocity of flow at the outlet of the pipe, right? So that's it. Now next we have is loss of head due to an obstruction in a pipe. Okay, so suppose there is a pipe, and in this pipe there is a certain obstruction. Okay, so this is basically the obstruction which I have shown here. And what happens whenever there is any obstruction present in the pipe, then the loss of energy will take place due to the reduction in the area of the cross section of the pipe where this obstruction is present. So what happens, since there is an obstruction present in the pipe, see at this region, that is the region where the obstruction is present, the area of the pipe, or the area, actually the area of the pipe is remaining same, but the cross section through which the flow is taking place is reducing. And what happens when the obstruction, when the fluid flow has come across this obstruction, then again what happens, the cross section of the pipe through which fluid is flowing is increases. Now due to this sudden enlargement, okay, due to this sudden enlargement, what happens, due to the sudden enlargement of the area of flow beyond this obstruction, the loss of head will take place. Okay, and the loss of head will take place, and it is given as how much? Vc minus v whole square divided by 2g. Now see, I have considered two sections, that is through the obstruction I have taken a section and marked it as 1, and through, and the second section is that which I have considered in the pipe where there is no obstruction. Okay, the cross section through which fluid flowing is normal, right, without any obstruction. So what is Vc? Vc is the velocity of flow at vena contracta. So vena contracta means the region of contraction. So this is my region of contraction, okay, in the pipe, and the velocity of flow in this region, in the region of vena contracta, that is the one which is passing through section 1, is taken as Vc, and the velocity, the normal velocity of flow that is occurring through this pipe, is taken as V. So the head loss between two sections is given as what? Vc. Vc is the velocity of flow in this contracted zone, minus V. V is the normal velocity of the fluid that is occurring, a fluid flow that is occurring through the pipe, divided by twice G. Okay, next we have the last two cases of minor energy loss or head loss. So the first, so the sixth case is loss of head due to bend in pipes. So what happens whenever there is any bend in pipe, the velocity of the flow will change. And why does it change? Due to the flow of the fluid getting separated from the boundary of the pipe, and also due to formation of eddies inside the pipe. So whenever there is a bend in pipe, what happens? Eddy formation, eddy currents take place, and also the flow somehow gets separated from the boundary of the pipe. In that case, what happens? Loss of head takes place due to this bends, and it is given by k into v square divided by 2g, where k is what? K is the coefficient of bend. Now these coefficients will already be given in your problem, or it will be given in your question, so you don't have to remember it or worry about it. Next, or the last case we have, is the loss of head in various pipe fittings. So loss of head in various pipe fittings like valves, like couplings, is given as again kv square divided by 2g, where k is the coefficient of pipe fitting and v is the velocity of flow. So that's it. These are the basic these are the classification of the major energy losses taking place through a pipe and the minor energy losses taking place through a pipe. The major energy losses mainly take place due to the friction or the resistive forces generating inside the pipe and the fluid flow, whereas minor energy losses takes place uh, due to certain bends or contraction or expansion of pipes as well as pipe fittings.